This video is a quick review of the fundamental theorem of calculus. It does not attempt to cover everything about the fundamental theorem of calculus, just kind of gives an overview that leads into the rest of this course. Okay, let's talk about a theoretical scenario. We're going to think about you launching a projectile straight up. We'll say from a height of 0. It doesn't matter a whole lot for what we're going to talk about. X is the time in seconds. And then I've divided the screen into two parts. On the left-hand side, the part we'll do in red, we're going to act like you have a formula for the function little f of x, which represents velocity of the projectile at any given time, and the velocity is measured in feet per second. On the right-hand side of the screen, capital F of x is going to represent the height of the projectile in feet. And so we're going to talk about how we would go about answering the two questions in each scenario. So on the left, you only have the formula for velocity. We're not going to actually get a formula, but we're going to act as though we have one. On the right-hand side of the screen, we're going to act like the only function we've got is the height function, and we don't know the velocity function. Okay, so the first question I want to look at is how fast is the projectile going, or is it moving 3 seconds after it's launched? And specifically, we're talking about the velocity. So if it's falling, we would get a negative value here. So I want to talk about how we would do this in each scenario. So thinking of the units, if we're talking about how fast in this scenario, we want feet per second. And so on number 1 on the left, we want feet per second, and the function gives us feet per second. Or we can think, okay, we want velocity and the function gives us velocity. So we would just plug in 3. So we would say, okay, that's f of 3. If you have a formula, you just plug it in. If you have a graph, you look at the graph and try to figure that out, and so on. On the right-hand half of the screen, we don't have the velocity function, we have the height function. So to get velocity, we want feet per second, which is, in this case, y divided by x. On the last video, we talked about that being the derivative. And so when we talk about the units of the derivative, those are y divided by x. Also in Calc 1, oops, problem 1 here, in Calc 1, you learn that the derivative of height is velocity. One way to think of that is in terms of the units, but here we're going to want f prime of 3, which means given a formula, you would take the derivative using techniques from Calc 1, and then you would plug 3 in. And a large part of Calc 1 is devoted to the fact that these two things are equal, that the derivative of height is velocity. More complicated things than that, obviously. We get into optimization, related rates, and things like that. But the derivative calculates the velocity. So f prime of 3 is the velocity at 3 in this case. And a big part of Calc 1 is why that relationship is so important. Problem 2, I want to look at how far. And I want to know, by that I want the displacement. Does it move? Does the projectile move from 2 seconds to 6 seconds? Okay, so how far does it move from 2 seconds to 6 seconds? So in this, displacement just means, okay, if it goes up 10 feet and then drops 2 feet, the displacement would be 8, and that's what we actually want here. So if it goes up 10 feet, drops 2 feet, it technically moved 12 feet, but what this question would want is 8 feet if it goes up 10 and down 2. So, okay, so in each scenario, one of these is easier than the other. On problem 2 on the left, we want feet. So you want an answer in terms of feet, but the function gives you feet per second. Well, feet here is feet per second times seconds but that's y times x. And so feet per second is y here, x here is seconds, so it's y times x, which in the last video we talked about being the integral. So in this case, we would want to calculate the integral from 2 to 6 of f of x dx. And we looked at approximating using a very simple Riemann sum in the last video. A lot of Calc 1 is devoted to more complicated ones and how to calculate that. But based on what we know kind of now, without talking about antiderivatives, the Riemann sum here would be something that's relatively complicated to calculate. On the problem on the right, if we want feet, that's y in this case, so that is just the function itself. So we would find f of 6, which would give us the height at 6 seconds. We would find f of 2, which would give us the height at 2 seconds. And then we would subtract, and that would give us the net change in height, which is the displacement. Okay, so thinking about this on problem 2, if you had a test where the question was asking how far did it go from 2 seconds to 6 seconds, or what's the displacement from 2 seconds to 6 seconds, and version A of the test had the version on the left, the velocity function, and version B had the height function, which version would you prefer for that question? So obviously you prefer the one on the right, because that involves just plugging in 6, plugging in 2, and subtracting. The one on the left involves doing a complicated Riemann sum. Well, if this is talking about the same projectile, then it's important that these two things are calculating the same number. And so the integral from 2 to 6 of little f of x dx is equal to capital F of 6 minus capital F of 2. That's real important, because the one on the right is a lot easier. And so the thing is, if that, then we have a problem like this. So let's say we were doing the integral from 2 to 6 of, say, negative 32x plus 106 dx. Okay, so if the velocity function was negative 32x plus 106, then look closely at what the statement above that's saying, where it says do f of 6 minus f of 2. It is not saying that you just plug in 6 and plug in 2 to that function and subtract. What it is saying is that you plug it into this other function. You plug it into the height function rather than the velocity function, and you subtract the height values. Well, that means that given the function little f of x, we need to find capital F of x. The relationship between the two is that little f of x is a derivative. So little f of x is the derivative of capital F of x. And then equivalently, capital F of x is the antiderivative, or an antiderivative, of little f of x. So if we're able to find an antiderivative, then we can plug 6 and 2 into that and subtract. So in this case, it turns out that negative 16x squared plus 106x plus 7 is an antiderivative of f of x. We can use that function and plug in 6, plug in 2, and subtract if we want to. So we could do negative 16 times 6 squared plus 106 times 6 plus 7 minus negative 16 times 2 squared plus 106 times 2 plus 7. And if we subtract those answers, let's do that real quick on a calculator. I'm getting negative 190, and so between 2 seconds and 6 seconds, it would actually fall 190 feet overall. But that's a way to calculate it. So I want to talk about a couple of things there. So the one thing to notice is that the plus 7 kind of comes out of nowhere. And so if you remember back to Calc 1, you can have what's called a plus c, and we'll talk more about that in the next video. But the derivative of 7 is 0. And so because of that, I could have put a 7 here, or I could have put 73 here. And it would not have affected the answer. The 73s would cancel. The 7s cancel. It doesn't affect answers when we're going from 2 to 6. What that would be in the scenario up here, the 7 would be the initial height. So if you launched from a height of 7 feet, then it would be 7. If we launched from a height of 73 feet, it'd be 73. If you launched from a height of 0 feet, which is what I think I said at the beginning of the video, we would just have plus 0 there or not put anything there. The point is it cancels out, and so it doesn't actually matter, but it would be the initial height. Okay, so the other thing I want to talk about is how do we go then from this function negative 32x plus 106 to this function negative 16x squared plus 106x plus 7, or plus 73. And so that's the process of finding an antiderivative. That's the first big topic in this course, is how to find antiderivatives. You've done some of that in Calc 1. But we're going to do a lot more detail of that in Calc 2. And so I want to end with one quick distinction. So if I'm looking for, say, the integral from 4 to 7 of x cubed dx versus this symbol, because of what we talked about up here, because of this relationship, which is a simplified version of the fundamental theorem of calculus, because of that relationship, these two symbols are very, very similar to each other. There's nothing before the fundamental theorem of calculus that would indicate they have anything to do with each other. Here, this is talking about the area under f of x equals x cubed from 4 to 7. This is talking about finding all antiderivatives. Of x cubed with respect to x. Because of the fundamental theorem of calculus, these two symbols look the same. Obviously, the only difference is there are no bounds. There's the 4 and the 7 are not on the problem on the right. They are otherwise unrelated. So it's not as earth-shattering in when you're talking about Calc 1 as to why these two are related to each other, because we choose the same symbols. But we choose the same symbols because of this huge result. Hopefully in Calc 1 you went into detail on the fundamental theorem of calculus. That's not the goal here. This is to give an intro to what we're going to be doing for the first part of Calculus 2. So we're going to focus on the ones on the right, which are called indefinite integrals. Those are problems to find the antiderivative. The ones on the left, definite integrals. Those are problems where we're trying to find an area or a net area. They're closely related to each other because of the fundamental theorem of calculus, but they are two distinct problems. Okay, so let's quickly look at the fundamental theorem of calculus itself. The fundamental theorem of calculus typically is given in two parts. The part we're talking about is this one. It says that if f is continuous on the closed interval ab, then the definite integral from a to b of f of x dx is equal to f of b minus f of a, where capital F is any antiderivative of little f. And so, like I said, the first big part of the course will be learning to find antiderivatives, and we'll pick that up in the next video. Thanks for watching.